They've been following you. They've been following you. It's a very turkey week for you. Okay, so we're going to go back to cross-validation. Okay, cross-validation is like taking your new car, or you're at the car lot, right? You're picking out a new car. You want to know which one is going to be best for you. So you take each car for a test drive, right? You look at a brand new Honda and you say, I want to take this car for a test drive. And there's also a brand new Kia and you say, I want to take this car for a test drive. And you think you're settled on both of those, but you also want to know which type of trimming and engine you want. So you might take out 2 different versions of the same Honda or 2 different versions of the same Kia, right? Mm-hmm. And then maybe there's another car that you're thinking about too. So that's what cross-validation is. You got 5 cars right here. Let's say you got your Honda, you got your Kia. Well, okay, no, that's not 5 cars.
It's one algorithm, and you're testing it on 5 different portions of one data set?
Yes.
Okay.
Very good. Yes, exactly. So yeah, that's what we do. We got one algorithm. Like, okay, let's put it this way. Testing. I'm trying to think. Okay, here's what you do. Let's just pretend these are instead of part of your data set, this is days of the week. Monday, Tuesday, Wednesday, Thursday, Friday. So you decide to take the Honda out for a spin on Friday, right? And you think it's pretty good, but you're like, you know, I don't know how the traffic is. I want to drive it once for every day of the week. And then I want to average that out and see how I feel. So you take the Honda out on Monday, you test drive it, take it out on Tuesday, Wednesday, and Thursday. So you've had 5 days in the Honda, and you say, okay, I kind of like that one. I'm going to see how I feel in the Kia. So you go back and you do the whole same thing again. Take the Kia out on a Friday, Monday, Tuesday, Wednesday, Thursday. So
why does it say train on the days that you're not on it?
Well, because it's not a perfect example.
Okay.
So
really, that's just, you're only in the test, you're really just the test.
Yeah, the test is what matters for this. So by
when people test, are they looking at specific parts of the data to try it on certain portions that may be of special interest and things like that?
No. I mean, you're supposed to randomize the data. Like, you're not supposed to, yeah, it has to be like one big chunk.
When they're all blue or something.
Yeah, no, that's like data manipulation. People do that a lot, like come up with dishonest results and stuff. But yeah, so you're basically, with cross-validation, you are test driving different algorithms. You are test driving, linear regression. You are test driving like a swoopy thing. You are test driving deep learning. You're test driving all these different algorithms to see which one performs the best. And you're not just doing it once with one of them, you're doing it 5 different times or 10 different times or however many. Just like, having a car, buying a new car is a big decision. So you want to test drive multiple times so you can average, your experience over those times. It's the same with models.
But you don't test it on the same day multiple times. You just test it once on every day.
Yes. Okay. Yeah. I mean, because this is all the same data set.
It's going to be the same answer, right? Every time. There's no...
It would, well, okay. So it could be the same answer or it could be a very different answer, depending on which part of the data set you use. So
right.
Let's say this is millions of points of data, right? And we randomized it completely. Before we split it out, we randomized it completely. So these are all just random buckets of data that we just split into 5 equal portions, right? So it's like the census data. It shows people's name and their age and where they live, right? And normally that would be in alphabetical order, right? But we randomized it. So it's just all over the place. You'll find an A and then a D and a Z, Q, R, people's first names starting with those letters or last names or whatever, completely random. And then after all that data is completely random in like a big old soup, we just chop it up into 5 different boxes or however many. I think 10 is customary, but I just wanted to use 5 for this example because it's simpler. So then once you have it chopped up into 5 different buckets, you train the model on these 4, right? The model is trained. We build a regression line or whatever we want from those 4, and then we quiz it using this. We say, do the results that we get from guessing on our regression line, do they match up with the results that we know to be true?
So you're trying to predict the last one, the last portion.
Mm-hmm. Yes. You try to predict, that's very good, yes. You try to predict the last portion of the data using the first 4 buckets. So then you see what the score is, and then you change which bucket you're using for testing, right? Okay, I'm trying to move this up a little bit. Okay. Are we good on cross-validation? Okay. Okay. All right. Okay. So we talked about selecting features, as in, remember our first data set where we were trying to figure out a person's weight from their height and all these other things. We decided that their address probably doesn't matter in terms of their height versus weight, and the number of pets that they have doesn't matter in terms of height versus weight. What we did there is called feature selection. What we're saying is, which columns do we want to keep and which ones do we want to throw away? Which columns are really important and which columns are not? For instance, if you're trying to guess somebody's weight, their height is probably very, very important, because the taller a person is, the more they weigh in most situations. Okay, but here is a more scientific approach, because sometimes a column might be numbers that you have no clue what they are, right? Like, say you're working in an industry that you're not familiar with, and one of the columns is like hex bolts in inventory, and you have no idea whether or not that's important to what you're trying to do. So one way of doing this is to figure out the variance. Variance is diversity of values in the column. Like someone gave a really good example. It might have been you, Will. Someone gave or Mike. Someone gave a good example of what if a person has pets. What if one of the columns is pets and they all have 2 pets, every single one of them? That's an example of low variance, because it's the same number all throughout the column, right? So if there is any variation in the data between the data and the test, or the data and the label, it is not due to that column. So that column does not matter. None of the changes are from that column because it's the same. There's not a lot of diversity of data in that column. So we can delete that column because it's a low variance column. It doesn't change a lot. So let's take a look at this. Which of these columns do you think has the lowest variance? Yep, very good. So we're saying height, we're trying to guess the weight from height, right? And there's a lot of variation over here, some variation over here, variation, but this one does not vary at all. Everybody drives 10 hours per week in this column. So if we're trying to guess this question mark from all of our data before it, do you think this matters? Nope, doesn't matter at all. So this is a column with low variance, numbers that don't change very much, so it is not important, and we can just delete it because they're probably not related. Okay.
So without even understanding what the data means in the column, you can just rule it out because it's not changing.
Yeah, exactly. Like, let's say you have a big table and you're trying to do machine learning on parts inventory, and every one of your parts comes from the same supplier, and that it comes in the data set that you got from the company. You could probably delete that column if every part comes from the same supplier, because it's just redundant information. It doesn't matter. Okay. So just like we said, low variance features are not important. High variance features are very important. If the data fluctuates a lot, then that's really, really important to look at. Like, you see these go up and down a lot, and height fluctuates a lot. So those ones are very important, especially if they fluctuate in accordance with the label, right? So as your height goes up, as your height changes, your weight changes too.
But there could be high variation, totally irrelevant information, like how many second cousins do you have?
That's a really good point. That's a very good point. I don't know how to answer that.
Okay, let's go on.
Okay. And also, like we talked about cross-validation, test driving, test drive it while you're removing features. So like you test drive your model with all the features and it's okay. It's got like an 80% accuracy. Then you delete one feature and the accuracy improves. And you say, oh great, this is awesome. Then you delete another feature, the accuracy drops, so you say, no, you gotta put that back in, right? Okay. All right, so the easy way to do this is just tell the computer, hey, eliminate low variance columns. Like you were talking about, how do we comb through this data set with millions of things? You can just program the computer to do it for you. And you can say, we need to delete all the columns with a variance threshold of this much. And we need to only keep the columns with high variance. And you're right, it could be that the variance is high and it's completely unrelated. So I'm not really sure how to deal with that problem. All right. Okay.
You wouldn't even have those columns anywhere around you if they were important, right? I mean, wouldn't you be able to just say that you don't? Why would they even be put in the data?
Good question. People are pretty lazy. That's why. What?
Is a human being deciding on the categories at the beginning of the process?
Well, sometimes. I mean, like, yeah, I mean, you're running a business and you have all of your accounting records. One column is debits, one column is credits, one column is, the payee involved, one column is the date. If someone is giving you data like that to do a machine learning experiment on, they will not know what data is relevant to what you do and what isn't. And often human-made data can be very flawed. There can be a lot of mistakes in it. So that's an additional problem to look out for. So, all right. Another one that sounds complicated, but it isn't really, is called dimension reduction or principal component analysis. What you do is, instead of working from the bottom up, like we said, instead of eliminating low variance columns, what you do is you find the maybe 2 or 3 or 4 highest variance columns, the ones that are most important to the problem. And how you do that is by graphing them. So if we have this graph, there are 2 dimensions which are really, really important to it. One of them is this way, and the second one is perpendicular to it, like that. You see how the highest variance is spread across this axis, and the second highest variance is spread across this axis, right? So those are the 2 principal components, or the most important parts of the data set. Those 2 columns right there. Okay.
So you could put any 2, or each one of those axes representing a column?
Yes.
Okay. So you could put any 2 columns in there?
Yes. You graph 2 columns. Yeah, you graph columns by themselves. Actually, one of the things that I didn't mention is when you're looking at your data set, you're going to want to use a lot of graphs, because a graph can help you see the relationships between different parts of the data set.
How do you get those graphs? I mean, is there like a database out there of sweet, like super cool graphs that represent important data?
I'm sure that there is. So you can search for something called data is beautiful, and that's helpful. But in Python, which is right now the most popular language for machine learning and artificial intelligence, there are lots of libraries that you can use where you just specify the axes that you want, and then it creates a really beautiful table for you. One of them is Matplotlib or Seaborn. So you guys are very, very smart. You're all asking very, very good questions. Okay. So we talked about that.
Seaborn?
Seaborn. Yeah. It's you can't just install it by itself. You have to install Python coding language and then use Seaborn, but you can look for it online. Seaborn for Python. Okay.
One more elimination of descriptors. Let's suppose that you have waist size and a skin caliper thickness.
Okay.
Chances are they're going to be somewhat similar. And if you were to do just a correlation between those 2, you might see a high degree of correlation between the size of the belly and the thickness of the skin flap.
That is a very good question.
You only need one out of two.
You're right. If you have two variables, two columns that are correlated with each other too strongly, you only need one of those columns. So like, let's say your address and your zip code. Those are kind of the same thing. They're very, very closely correlated with each other and you only need one. Or like number of cats and level of insanity. Those are two very, very closely related variables, so you would only need one. So that was a very good point. Did you just figure that out, or did you already know?
No, that's
okay.
something that we use also.
Okay, because that's a very good point. Okay, so algorithms. An algorithm is a program for processing data. It is, after you give the computer a data set, you have to tell it what to do. Otherwise, it doesn't know what to do with it. So an algorithm is telling the computer what to do with it. You'll hear this word thrown around a lot. A lot of people will try to impress you and make you think that they're smart by saying this word. If they say that, ask them what they mean by algorithm. Or, another couple questions are, everybody says artificial intelligence this, artificial intelligence that. I heard about an AI toothbrush. I heard about AI shoes, which is kind of ridiculous. So if somebody tells you that their product is an artificial intelligence product, or that they did something with artificial intelligence, ask them, okay, well, what algorithm are you using? What model are you using? What's your accuracy? What's your data set? These are all questions that you guys know about now. You know what those words mean because we went through it. Okay, so algorithms. Oh, this is Al Gore, and he is beating out a rhythm. An algorithm is a plan for learning from data, just like we said. Okay, so K-nearest neighbors is one type of algorithm. It's like we were talking about the census. What if we had a big data set of the census, and let's say you pick me on the census. I want to know who my nearest neighbors are. I want to know who lives around me. So I can look on the map and I can draw a circle around the people who live near me, right? I look at the census data, I look at their names, and then I draw a circle around myself. So that's just one example. But let's say you do the same thing. And then you want to find out who lives nearest to you, so you draw a circle around your nearest neighbors. Okay? So K-nearest neighbors is you group your data into clusters.
Based on a number?
Yes, based on which points are closest to each other.
And well, how many points are you considering? All of them? Or is that what K it represents?
K
is the smaller circle?
K is the number of circles.
Oh.
So like there are 4 people in this class. We would say, okay, 4 people want to figure out who their nearest neighbors are. And so of the entire census, we would have to divide it up 4 ways. I would get a group of my nearest neighbors. You get a group of yours, and so forth. Does that make sense?
Yeah, they'd all be the same in this case, though? But in a different order?
They would have to be a little bit different. Okay, let's use a different example. There are all these desks in this class, right? And let's say all of us get to own a certain number of desks. We get to own desks. So I get to pick the desks that are closest to me, right? So I obviously get these 3, and I get this one. Mike gets this desk, and he gets that desk too. Probably these 2 as well. Will, you definitely get the desk that you're sitting at, and the one to your right, you would get the desk in front of you and the one behind you, right? So we just used the K-nearest neighbors algorithm to classify who gets what desk, right? Okay.
And it does that with values in a column.
Yes, you can do it in just one columm. You can do it in 2 columns. You can do it in any number of columns. You can do it in,
So that really breaks the number of. Is that like how many groups do you get out of that?
You specify it at the beginning.
Oh, okay.
So like we say, okay, all the desks in this room, we want to divide them up into 4 different groups because there are 4 of us, right? So we choose K is equal to 4. But the example that we're doing right now on the slides, we're going to choose 3. So, okay, so so we've got this graph. It's a 2-dimensional graph. Where do you guys think the groups are? If you're just clustering these guys into the closest groups together, and we've only got three groups, where do you think they're going to be? Yeah, like this one right there.
2.5, 10, and 20.
Right? Yes, very good, Mike, you're a very smart person. All right, so yeah, the groups would be right there, and right there. See, you're just clustering them. Okay, because these guys are nearest neighbors to each other, right? Okay, here's a different type of the same thing with a ridiculous name. It's called hierarchical agglomerative clustering, which if you can remember that, you're going to sound very smart for the rest of your life. Just throw it into a conversation. If you ever feel comfortable or you're on a date, just say, oh, it's just like hierarchical agglomerative clustering. But so anyways, it's kind of similar. You start with every point in its own group, and then you merge together groups that are close together. Like, for instance, this would not do very well with a nearest neighbors. You can see that there are 3 groups right here. You can see just with your eyes that the pattern is obviously 3 distinct groups. But if you do KNearest Neighbors, it's going to do it incorrectly. It's going to say, okay, well, this point is close to these guys. This point should be in this group, and that point should be in that group. That's just how it does it. It clusters the ones that are closest together instead of individual patterns. So with hierarchical agglomerative clustering, you start off with each point in its own group, right? Then you start merging the groups. And then you start merging them. And then you stop right there. You see? You see how it's completely different from KNearest Neighbors?
Yeah.
Because it can do patterns that are more like this. It can do like spiral patterns. You can do circles. It's just a different way of doing things. Okay. But if you don't stop at the right point, then you're going to put everything in one group, which is useless. So, all right, let me see. Okay, now we're going to talk about deep learning. Okay, so deep learning is the fun part. Deep learning is based on how the human brain works, which is very interesting. Artificial intelligence is trying to mimic human intelligence now. So we're going to talk a little bit about how the brain works. Okay, inside your brain, you have a ton of things called neurons, right? That's what your brain is made up of. Tons and tons of these tiny little things called neurons. They're just electrical connectors for your brain. So let's just pretend right now, this dot's a neuron. It's inside your brain. How it works is it zaps electricity over to another neuron. And that's how they communicate. They shoot electricity, right? So, and then if the electrical signal is strong enough coming from this guy, then the second one will zap to another, right? But if it's not strong enough, then it won't zap anybody. It just stops right there. Neuron number 1 shoots out a tiny little bit of electricity, goes to the next neuron, and it doesn't go anywhere. It doesn't zap out anywhere. Whereas if it shoots out a lot of electricity, the second one says, okay, that's enough, I'm going to shoot out some more, right? That's how neurons work. It's like kind of like trains in a pathway. So
It's got to pass. It's got to be a certain strength.
yeah, it's like a gate. Like a gate, you have to be strong enough to push
It
open.
could be way more too, and the second one would send out the same signal. The first signal could be 10 times that. The second one would still be the same.
There's let's come back to that for right now. There are equations for how strong the second signal is. But yes, so if it's strong enough, it will send out a signal. You guys are all really smart in this class. I'm really liking it. You guys come up with very good questions. Okay, so if it's too small, it won't pass the gate. All right, so there's something called a synapse, which is a gateway between neurons. It's the pathway between neurons. And as you keep using this synapse, it gets thicker. And if it gets thicker, then it transmits a bigger charge. Even if a small charge comes out of this one, if your synapse is big, the charge is going to come out big on the other end. This is how we learn. Your synapses get thicker. So let's say I start out juggling one day. I'm terrible at it. That's because the synapses in my brain that are associated with juggling are not thick. I don't know how to do it yet. As I keep practicing, as I keep getting better at juggling, the synapses associated with juggling, the ones that I use when I'm juggling, get thicker through exercise. So that even if this neuron fires a little tiny guy, this one will still fire, right? So a synapse is kind of like a multiplier of the first electrical shot, right? So if you have a big one, big electrical shock, it's always going to go through. If you have a small electrical shock, it might go through if your synapse is bigger. And synapses get bigger through practice and use. It's like if you grow up doing math, if you've done math a lot, those synapses are very strong, they're very thick in your brain, and it's very easy for you to get back into that math mode.
It's interesting to think about how you prune them down too, though, because you don't, if you do the wrong thing over and over again, or if you're you have to tell yourself that it's wrong, and that's kind of like I don't know how that plays into the whole deep learning situation, but your brain's ability to tell your, I guess, motor cortex that it's not doing the right thing.
Yeah, that's a good question. It's kind of like between the conscious and unconscious mind or something. I'm not really sure how. I feel like if you know that you're doing the wrong thing, then you will consciously choose to do something different, and then that new action will change how your synapses are working. Like for example, I have a song that I wrote 12 years ago, and I wrote it before I learned how to sing, and I sang it hundreds of times. Then after I learned how to sing, I could sing songs really well, but every time I try to sing that song, I revert back to my old really bad singing habits because my synapses have grown in that direction exactly. So you're right, you can learn in the wrong direction.
Back into the old muscle memory.
Yep, and it's just with that song. Every other song I can sing correctly. All right, so this is an artificial brain. We talked about a real brain. This is a real brain. This is an artificial brain. It's similar, it just has different terminology. This is a neuron, just like in a brain, but instead of a synapse, we call it a weight, right? And instead of sending electricity, we send numbers. So in this one, we're going to send the number 4. This neuron shoots out the number 4 instead of, an electric shock. So, and then if that number is big enough, then just like the electricity, it shoots out another number, right? And there's an equation in here. We'll get to that in a second. So, let's go back to weights a little bit. If the weight is thick, or in other words, if this weight is a big number, then it's going to multiply 4. So 4 will show up here bigger than 4. Just like, the electricity goes through a thicker synapse and it shows up bigger. Same for the number 4. So if we have a weight down here, the 4 could show up as an 8. Whereas if the weight is small, like 0.5 or something, then this 4 would only show up as a 2, right? And if it's smaller, then it might not pass muster and it might not activate this guy. It might not send out anything.
It just stops.
Yeah, it just stops right there. Or maybe it'll send out a 0. I'm not really sure, but it just stops right there. Okay, so let's talk about what's the decision maker. Why do some numbers get through and some numbers don't? It's because inside of this neuron, this artificial neuron, there's an equation. Like here's one of the decision processes. This is just an example. Okay, if I get a number bigger than 2, I will output that number plus 1. Thank you. If I get a number bigger than 2, I will output that number plus 1. Otherwise, I'm not going to put out anything. If it's lower than 2, I will put out nothing. If it's bigger than 2, I will output that number plus 1. Okay, so now we've got our neuron. Is this number bigger than 2?
Yes.
Yes. So it goes into here. The equation was, if I get a number bigger than 2, I will output that number plus 1.
Yeah.
So what's it going to put out?
5.
Very good, 5. Very good. And if there is a weight right here, as we talked about synapses influence things, if there is a weight, it will get multiplied by that weight. And it will go on to the next. It will go on to the next neuron.
So you would consider the synapses as numbers or weights? What was that analogy?
Yes, the synapses in your brain, right, are the same as weights.
Weights.
That's what they're called. They're called
And
weights.
the electricity is the number?
Yes, the electricity is the number. Yes, very good. So one thing that's interesting is in the artificial neural networks, this guy right here does not change. This guy stays the same throughout training. The equation that we have inside of the neuron, that always stays the same, right? But when you are training, the weights change, right? So if we don't want 5 to get through to the next one, then we could just say, okay, this weight is 0.001. So then no matter what this guy puts out, even if it's a 5, it's always going to be a really, really small number and it's not going to get through to the next one. So in artificial intelligence, what you are learning, what is changing is the weights. The thing that you multiply the output by, right? Because this equation does not change. Only the weights do.
So what you're talking about here is not hardware, it's software.
Software, yes. Software that emulates hardware. Okay, so, and here's another example. We said if it's less than 2, we're not going to let it go through, right? So less than 2 doesn't go through. All right, so we just talked about this is what one neuron does when it's communicating with another one. Actual artificial intelligence networks don't look like that though. They look like this. They have a bunch of neurons connecting to each other. And then they have those neurons connecting back and forth. I didn't want to show you this, guys, at first because it's very intimidating and it's very confusing. But this is how actual neural networks connect to each other. They have all of these synapses right here. And remember, these guys do not change. The equation inside of these guys do not change. The weights do. The weights change. So, okay, how does this work? So when you change those weights, what it's doing is it is approximating a function. Imagine this. You have a friend who can make like sandcastles, right? And you say, I want you to make a sandcastle of me. Like, I just want you to make my body lying down on the sand, like perfect in my face. So he's going to use individual grains of sand to build this thing, and it's going to look like you. It obviously won't be you, but it'll look close enough given that it's made out of sand. That is what a neural network does. When you change all of these weights, it can make it so that your input coming from here will match your output. That's what an artificial neural network tries to do.
Your desired output.
Yes, your desired output. So like we input a picture of a cat here, remember all those numbers, and then we make it match an output over here. So let's say, or like a dog photo too. Like,
Who changes the weights? Is that the algorithm?
It's the computer. The computer does it automatically. It goes through this process called training where it randomizes the weights first, right? And then you have like a dog photo and a cat photo, right? And then you train it and you've got cat and dog right here. And it trains it until the error is reduced. Remember how we had those points on the line? And we said, you know, the line is fitted so that the error is minimized, so that it's closest to all the points. Okay, well what this does is it changes the weights until the input matches the output. We tell it what the input is, we tell it what the output is, and then it changes the weights until those things match. The theory being that if we put in a new similar input, then it will match it to the correct output. Does that make sense?
If you can change the weights properly.
Yes, it does those on its own. You
Oh,
can
does it? Oh, okay.
you can set parameters to how.
That's what the algorithm does. Is it's the method of updating the weights.
Actually, deep learning is the algorithm.
Oh, okay.
It's the instructions for data, for what to do with the data.
It's always the same.
Well, no, there are different types of deep learning, but it always involves an artificial neural network. So deep learning is the algorithm, but how the weights are adjusted is something else. It's called like a hyperparameter is what it's called, but it's basically just tuning this. Remember how we talked about cars? You want to buy a Honda, you want to buy a Kia, but there are different models of Honda. There are different types of the same model of Honda. Like one has extra air conditioning, one has leather seats. That's like deep learning, this model, and the one with leather seats is a different hyperparameter, so it changes how these weights learn. Yeah, and another one is a different hyperparameter, so it changes how these weights learn.
Are there hyperparameters that work in different areas of the network?
No, usually one hyperparameter. Shoot. Okay, you can't. These are layers. This is a layer. This is a layer, right? And you can set one hyperparameter for an entire layer, right? But you can't go deeper than that. You can't set one hyperparameter for this, and then that.
Just for the connection between, the top one there and the bottom one or whatever.
Well, all of
Specific connections.
yeah, all of these would have to be the same hyperparameter,
Of course you can. Yeah.
and all these would have to be the same hyperparameter, and you can also set hyperparameters for the whole function. Why they're called hyperparameters is because parameters are the weights, right? So if this is 0.05, 8, 0.1, those are all parameters. A hyperparameter is above. Hyper means above, more. Hyperactive is you're more than active. So a hyperparameter is kind of like God looking down on this thing. It doesn't touch the weights, but it says, I'm only going to let you weights do so much. I'm only going to let you do this, and I'm only going to let you do that. And it also says, hey, I'm going to set up rules for you guys. So a hyperparameter is kind of the rules for the neural network, whereas a parameter is the actual data within the neural network. It's the actual solution inside of it. Okay.
So are there, is this to the point where there are libraries available of different deep learning algorithms, and you could do answer like a wizard to answer questions, and it would automatically. That's all out there already.
Yeah. Actually, I've used one. They make it easy to create one. Like you can put in like your standard operating procedures manual from your company, and then you can make a chat bot so people can ask questions and the chat bot can answer using the standard operating procedures manual. But yeah, there are lots of machine learning libraries out there. One is called TensorFlow. That's the most popular in the world right now. Another one is called PyTorch, and there's another one called Keras, Keras, which is a simplified version. And yeah, those are for making your own artificial neural networks.
So you could you have your data set, and you could pick what one looked like. It would analyze the data the way you could set it up to do what you want it to do.
Mm-hmm. Yeah.
And you wouldn't have to program it in Python or anything like that.
There are some programs where you can just drag and drop and make your own model that way. From my experience, they're not very good. For right now, you're going to have to use Python to make your own neural network.
Yeah, like have to wait 5 more years.
Yeah, probably around then. Right now, with some libraries, it's easier. You say, start neural network, layer 1 is this, layer 2 is this, layer 3 is this, layer 4 is this, and here's the output. So it's a little bit easier, but it's definitely not to the point where you can drag and drop. I wish it were, because that would be really fun. But okay, so we were talking about function approximation.
Yes, I'm sure that there's somebody out there has an interface like that.
They're working on it.
Yeah, I mean, I've seen two. There's one called Orange, and there's another one called Deep Learning Studio, and I don't really like either of them, so I can't really.
What do you use, like a Python development environment?
Yeah. Okay. So I use Python, and there's this online workbook called Colab, which is amazing. It's like go to like collaboratory.google.com. It's like a really high-powered computer in your browser. So you can type, you can program, you can run programs. It's all in your browser. And so you don't have to install anything ever. It's pretty incredible. I love it.
It's called Colab?
Yes, COLAB.
And it's the creativity, intelligence, change the way you work. So it's basically like a virtual computer.
Yep, virtual computer.
You pay for it?
Nope, it's free. I love it. It even has a GPU acceleration. So if your computer doesn't have a GPU, you can turn on a GPU.
What's it called?
Colab.
C-O-hyphen-L-A-B?
COLAB.
Okay.
Oh, Google Colab.
Yeah. Actually, in fact, if we have some extra time, I will show you guys some really cool examples of Google Colab where you can generate your own art. Yeah, okay. So we're going to talk about function approximation. Here's a very simple function. Y equals x plus 2. Anything you put into it as x, it's going to add 2. So if x equals 1, y would equal 3. Perfect. Okay. Input is x, or input x equals 1, output y equals 3. And these are all, part of that equation. 5 plus 2 is 7. 10 plus 2 is 12, right? So with a deep neural network, instead of, like with normal functions, what you're trying to do is you have the function, you have the input, and you want to get the output. That's what a normal function does, right? With deep learning, you have both the input and the output, and you want to know what the function is, right? Deep learning figures out what the function is, and that's why it's so important. Like we talked about, the height versus weight thing. So what we can do is we have our inputs and we have our outputs, and the deep neural network can figure out the function. Like let's say we put over here as the input somebody's height, and then over here we put the output is their weight. So we would train the deep neural network. We would say, okay, here's our input, here's our output, now figure it out. And then it would figure out an equation for us. So that way, when we have a new input, when we put in a new person's height, it will give us a good output for their weight, right? So that's what deep learning is.
Without ever giving it the formula.
We don't give it the formula. It figures it out on its own. And it can be pretty incredible because it can figure out really, really complicated formulas sometimes. Formulas that we wouldn't be able to figure out in our heads. Oh, actually, this is really cool. Somebody figured out an artificial intelligence that can picture how you look based on your voice. That's not something we could never come up with an equation for that.
It's pretty good too.
Yeah, right? Yeah, well, the faces are fuzzy, but it can like tell ethnicity and kind of like what the center of your face looks like. There was also one Chinese researcher who found that he could tell from a person's face, from a photo of their face, whether they had criminal tendencies or not. Pretty cool, pretty cool.
Just to go back to the weight and the inputs on that, your diagram for the neuron was a single input, but if the neuron was actually the height, the sex, the what are the other pieces of information? Maybe the stomach diameter, etc. And then on the output of that training system would have been for each individual what their weight was, and you knew what all of the inputs were over here. You could train the neural network, I guess, to take those inputs and predict that weight over here.
Yes.
From multiple inputs besides just height.
Okay, yes. And the reason why I had only one input on here is because we have a way of compressing, that entire chart. We have a way of compressing that entire chart into one object, into one block. It's called a tensor, which I don't want you to feel confused. You know what a matrix is, right? It's just a graph like we had way back.
Is that table we had?
Yeah, that table that we had, that's a matrix. It's just data in more than one dimension, right? A tensor is data in 3 dimensions, right?
Or more.
Yeah, 3 or more dimensions. So you've got like a line of data that's just a line. Then you've got a table, 2 dimensions, that's a matrix. And then if it's in 3 or more dimensions, that's called a tensor.
That's the TPU you were talking about.
Yes,
Yeah.
dude, you are on top of it. My goodness, yes. So that is why we only have one input right here, because we compress all of the data into one block. I imagine it as a cube called a tensor. We put all of that data into this neuron, and then we map it to an output over here. Right?
So you're,
Okay, so
you're considering the network a tensor.
no, the network is not a tensor. The data that we put into the network is a tensor. Like we had that table, right? What we take is we take one of the records, like one of the people, and we package them up. into like all of the columns for that one person, we package them up into a tensor.
So
Right.
It's like what would you consider it? Like a class, or if it was a program in programming? Classes?
A tensor?
Yeah.
Not necessarily. It's like
Or objects.
okay. So let's say Mike eats paper. He loves eating paper, and I have a bunch of strips of paper. Right? I have a bunch of strips of paper, but he's very finicky. He will not eat strips of paper. So I have to fold them into like a cube before he will eat them, right? So I fold a piece of paper into a cube and I hand it to Mike and he eats it. I fold a string of paper into a cube and then Mike eats it. Because those strings are like each row in the column, or each row in the table, right? So each row has to be turned into a cube, a multi-dimensional array.
So it's really just picky.
Yes, it's very picky. Yes, neural networks are very picky. So, yes. All right. Okay, so, all right. So now we're going to talk about training a neural network.
Before you go on, that was kind of a breakthrough for me in understanding this, the idea of, and so I wrote out this sentence that I'd like to read to you and tell me if it's right or if it's
absolutely.
corrected.
Uh-huh.
So you feed a bunch of data into a computer,
Yep.
and an algorithm learns the relationships between the data points, so that when you give it new data points, it can predict the missing data points in the new stream of data.
Yes, because yes, it predicts the relationship between the input and the output. So you
basically the x plus y, you just tell it, okay, these are the numbers that go together. Now I'm putting in 26. What's the missing one?
Yes, exactly. Perfect.
Without programming it that, okay, x plus y equals whatever.
That's the fun part about it. You don't have to program the function in. You just tell it, figure out a function. And then from then on, you can take advantage of that. So, and like we said before, if you overfit, then that function is not going to work in real life. It's only going to work on the same data. But if you make it fit so it can generalize, then new data coming in will give you new answers. So, all right. So this is kind of how it works. Picture of cat, input, cat, picture snake, picture of a person, very, very ugly person. I remember this picture's been around since like the 1990s.
Yeah, what is that? I've seen that before.
What I think it is back in the 90s, there was this software that came out for editing people's faces to look like this. And I think this was on the box. And I think that this image is just so compelling that it stuck around. So as we said, a neural network creates a function, right? So this is just a huge number of numbers, right? It's just a bunch of pixels. Same for this, it's just a bunch of pixels. Computer just sees these as collections of numbers. And then we have person, we have snake, and we have cat. So we're telling the computer, we want you to make an equation that connects this input to that output. We want you to make an equation that connects this input to that output, and this one to that output. And believe it or not, a computer can. It can make an equation that turns this into that, right?
Someone's getting that data.
What?
Somebody's going to get the data, like all the data from everything.
Yeah, and put it into a machine and then they can predict everything. Actually, Google does this thing that, I don't know whether you feel it's creepy or not, but what Google does is in their search results, it's so accurate because they know you.
Yeah.
Like they know what you've searched for in the past, and so they can figure out what you're trying to get at very quickly, which is kind of cool because it does really, really help. But at the same time, it's, I don't know if I want Google knowing that about me. Okay, so you've trained this brain. You said, okay, we made an equation that equates this collection of numbers to the word cat. So then we put in a new photo of the cat, and this brain is already trained, so the brain is going to say, oh, okay, I think that's a cat with toilet paper on its head. Okay, oh, this is really cool. Okay, go to talktotransformer.com.
Literally right now?
Yes, please. Okay, so are you guys at talktransformer.com? Okay, so this is an algorithm called GPT-2. It was trained on millions of websites. A lot of them were news websites. The creators of it thought it was too dangerous to release because it can generate text that looks human, in particular news articles. They thought that if they released this, it would be used to spam the internet with fake news. So go ahead and type something in the box and press enter to see what happens. Like, I particularly recommend something that sounds like a news article. Like, Donald Trump's pants fall down at G2 summit or something like that. Or maybe Kim Jong-un contracts hay fever. And once you've done that, let me know if somebody has a particularly good one that they'd like to read aloud.
Pretty funny.
You want to read it?
Yeah, so the second structure was built, and then it was more sophisticated than the first. And then they go, in the second structure, they used harnesses and ropes to lift the roof of the pyramid and hold it up. These ropes were strung between the curved supports and the sides of the pyramid. The foundations of these lower structures were constructed from large blocks of stone. Yeah.
To me, that sounds real. That sounds like a human wrote it. One of the things that's really interesting is when you type in something that sounds like a news article, and it will confidently make up facts that do not exist. Like the last class, I showed you guys somebody. It talked about how Rachel somebody was the head of this company or this nonprofit, and she's doing a great job. And I don't think that person even existed. I don't think she was the head of that nonprofit, but it sounds true. It all sounds like it's saying it confidently. I just think this one's incredible because it sounds so human-like. All right, this is what I was talking about. This is art that I generated with artificial intelligence. All I did was just type in a number. There are 225 styles in this particular thing. And I just typed in, I think 73, and I liked how it looked. And
what side is that?
I'll show it to you guys at the end of it. It's one of mine.
Okay. Don't worry, you don't have to show us all your secret sides.
No, it's cool. I don't know if I have the link. I'll try to, if towards the end of the class, if we have time, I'll show you guys the link and I'll show you how to do this. Okay, here's another image. I like that one. I really like that one. That one's pretty. So it's just like a bunch of different styles, and all I did was just enter a number and it generated a cool new image. And every time you generate an image, it's different. It's got the same colors, but the shape and everything is very different. Okay, so let me see. We already did GPT-2. Oh, this one is really cool too. Okay, this is called Mat2Vec. It was created by researchers working with Toyota. It is a machine that actually discovers knowledge. They were looking for a type of, thermoconductors or thermoelectric materials. And so what they did is they fed 5 million papers about thermoelectric materials into this machine. And it was able to discover, I think, like 40 new materials just from those papers. It was able to advance science just by reading science and creating new stuff. Okay, what do we have? Okay. Deep reinforcement learning. I'm going to give you guys another 5-minute break while I prepare the next slides, and then we'll come back and we'll talk about reinforcement learning, which is what somebody, I think Jonathan might have been talking about. Mario, was that you, Will?
No.
Okay.
No, that was Jonathan.
Okay, yeah. So we're going to talk about how to beat video games using reinforcement learning. Go ahead and take a 5-minute break.